Alright, so this is 6.2, the dot product of vectors. In this lesson, we're going to talk about a few things. We're going to talk about dot products. We're going to talk about angles between vectors, orthogonal vectors, projecting one vector onto another, and we're going to work through a bunch of problems to really get a feel of how this works. So, the first thing we need to see is just what a dot product is. Now, if I have a vector, let's say u, and another vector, let's say w, I use w instead of v because I think it's easier to see on my handwriting. We're going to say this is the dot product of u and w, the combination of them, the effect of one on the other, will be u sub 1 times w sub 1 plus u sub 2 times w sub 2. And what this means is if we assigned u to u1 and u2, not the band, just the expression, if this is that vector and vector w was w1, w2, we would write it, we would multiply the x's together, and then we're going to multiply the y's together, and we're going to add them together. We discussed this a little bit in class, but this is the way that it works, and for the sake of time, we'll move on. We're also going to say that this equals another thing as well. This equals the magnitude of u, times the magnitude of w, times the cosine of theta. And when I say theta, what I'm actually saying is the angle between the vectors. Angle between vectors u and v, or w in this case. Now let's unpack what we're talking about here. Or maybe perhaps more accurately, let's unpack this with an example. Let's just jump right into example 1. This is example 1 in our books. Or not example 1, this is exercise 1 in the books. We have a vector u, that is the points 5, that goes to the point 5, 3. And we have a vector w that goes to the points 12, 4. And it asks us to find the dot product of u and w. Well, in the book it says u and v, but for the sake of this example, we used u and w. Now to this, it's really simple. I mean, in essence, perhaps, we have to take this x value of u and the x value of w, we're going to multiply them together. So we'll go ahead and say 5 times 12 would be our first bit. And we're going to add that to, the y values, the combination of the y values. That would be added to 3 times 4. Okay, so if we work that out, that becomes something, that just works out to 60 plus 12, which gives us simply 72. And that easy peasy lemon squeezy is our answer. Great. And that's literally all we do for dot products of vectors. This is important to know because this is a foundational building block of the rest of the lesson. So now if we know how to do the dot product of vectors, how to take the effect of one vector and multiply it onto another vector, we're going to also figure out the angle between these two vectors through another means of expressing it. Now let's look at this. So let's look at this second bit down here. Let's use this purple color. This second bit. The magnitude of u times the magnitude of w equals the cosine of theta. What this is saying is that if I took the magnitude of u and the magnitude of w and multiplied them together, those are two scalar numbers. Those are like in the same way that we just found the dot product is a scalar number. Those would be two scalar numbers. It's the size of u times the size of w, and multiply that by the cosine of the angle between the two vectors, we would get the dot products. So if we wanted to find the angle between two vectors, let's say, for example, we were given problem number 13. Problem number 13 are exercises. And it asks to find the angle theta between these two vectors. It gives us an angle, say, it says -4, -3. And it also gives us a second angle, it's called w, that is -1, 5, and it asks us to find the angle between these two vectors. Now we can use dot products to solve this. We know the dot product of we know how to find the dot product of u and w, and we know the that equals the magnitude of u times the magnitude of w times cosine of theta. So we can just plug those things in and solve for theta. Here's how we do it. So we have u, and we have w. Let's use a different color because that's no longer part of the problem. Let's see. Let's use, we know that the dot product of u and w equals the magnitude of u times the magnitude of w times cosine theta times, let's use gold, times cosine theta. Great. So let's first figure out, to solve this, we're going to try to solve for this angle between the vectors, this cosine of theta, and we will start just by plugging in values and figuring out what we can figure out. Let's start with finding the dot product of u and w. Well, that would be simply, or perhaps it'll be reasonably, -4 times -1, we'll multiply the x's, that'll be 4, plus -3 times 5, that'll be a -15. That'll be that'll be the dot product of these two vectors. That's this first bit. Then we're going to find the magnitude of u. Now, if you want to find the magnitude of a number, that's something we've talked about before. I think it's on page 460 something. The magnitude. Let's see if I can find it real quickly. The magnitude of a vector, then yes, the magnitude of a vector comes straight out of the Pythagorean theorem, and if you're looking for a formula for it to help prove it to yourself, that is on page 504. To put it quite simply, the magnitude of anything, again, just as a refresher, the magnitude of anything is, and if u equals u1, the vector u1, u2, then it equals a square root of u1 squared plus u2 squared. You might recognize that as being part of the Pythagorean theorem. It looks pretty similar. And again, if you'd like to know more about it, just make sure you ask a teacher. Great. So we have the magnitude of u. The magnitude of u in this case would be the square root of -4 squared plus -3 squared. Great. And we're going to multiply that. By the magnitude of w. The magnitude of w would be -1 squared plus 5 squared. Great. Finally, we'll multiply all this by the cosine of theta, and work from here. So back to the beginning, 4 plus -15, that would be -11. And then the first square roots, that'd be 16, the square root of 16 plus 9, and then furthermore, we would say this is the second times the square roots of 1 plus 25 times the cosine of theta. All right. Well, this 16 plus 9, that's just 25. This 1 plus 25 is just 26. Great. So we can say this is, we can go ahead and try to solve this even further. If we say it's -11 equals, that'd be the square root of 25, that's just 5, times the square root of 26. Cosine theta. Cosine theta. Alrighty. So we'll go ahead and divide both sides by 5 times the square root of 26. So that gives us, I'm going to switch the sides, so cosine of theta equals, this would be a -11 divided by 5 times the square root of 26. Finally, if we want to find theta, again, we're just solving for theta, so we'd say theta equals, and we're going to use the inverse cosine because we just inverted the cosine, inverse cosine of all that business. I'll just use the same color for speed, -11 over 5 times the square root of 26. Now, if you were to solve this, you'd get an answer that should be, roughly, you should get theta equals, if you plug this into your calculator, you'd get something along the lines of theta equals 115.6 degrees. And that would be our answer. Great. So that's how we do problems like that in finding the angles between the vectors. But there's more tools that come from using these properties. So for example, if you go back to page 514, you'll notice that we have that there's a bunch of properties about dot products, and you'll also see that these properties about dot products are very, very much just like they're almost exactly the same as simply, say, multiplication properties. For example, u times v w equals w times u. That makes sense. The dot product of u and w equals w times u. Dot product of w and u. And we can know things like, well, the 0 times the dot product of 0 and u is just 0. We can see that. We could probably see that if you multiply 0 by an entire vector on both sides, you'd get 0, 0, which is just 0. So let's see. But there's one that's particularly interesting, and that's this one. It's the dot product of u and u equals the magnitude of u squared. The only reason why this is very different from normal is that it's got this magnitude in here. But it's important to point out because it'll really drastically affect your answer. And what we're saying is that the dot product of this thing together squared equals the dot product of u squared, in a sense, is, you can't just say u times u equals u squared. You normally think that. That's not what's happening. You've got to stick that magnitude in there, because we're saying how big is this? We're taking the effective one and we're multiplying it upon itself, which wouldn't make much sense unless you have this magnitude. Here's a way to really see it play out. We're going to look at example. Let's see, what example number is this? This is example number 9. We need to use the dot product in order to find u. So it gives us, in example number 9, it gives us u as 5, negative 12, and it says use the dot product in order to find the magnitude of u. Well, we know, and this is very helpful, we know that the dot product of u and u, let's actually make this blue. This is something you should write down in your notebook. The dot product of u and u equals the magnitude of u squared. And if that is the case, well, if we want to find the magnitude of u, well, then we'll just plug in u everywhere we see u and just solve for the magnitude of u. So we'll plug in u, so we get 5, negative 12, the dot product of that with 5, negative 12, excuse me, equals the magnitude of u squared. We can go ahead and square root both sides. Get something interesting. We'll have the magnitude of, we have 5, negative 12, dot product did with 5, negative 12, and that equals the magnitude of u. Excellent. Let's go ahead and solve this bad boy. We'll have the square roots of the, let's define a dot product. We're going to multiply the x's together, so that is 25. And then we're going to add to that the y's multiplied together. That'd be 12 squared. That'd be negative 12 squared. Or another way to write that, that's just simply 144. That's 144 equals the magnitude of u. We're going to add these together. That gives us the square root of 25 plus 144. That is 169. Yes, equals the magnitude of u. And the square root of 169, if you plug it into your calculator, or if you just happen to know your times table is up to 13, I don't expect you, but if you did, that'd be really cool. It'd be, you know that the 13 squared is 169, so 13 equals our magnitude of u, and that is our answer for number 9. Great. So now we know, now we know that the dot products and and the different forms of what dot product means, we also know now some helpful tools that the dot product offers and how it looks a lot like it works very, very similarly to just multiplication. But there's something else we needed to notice, and the next part is seeing really some cool properties about dot products and them working together. To do this, we're going to first look at a little example. Let's say I had an axis. Let's say I had two vectors, and they went from here to here. Alrighty, and let's say this one vector, let's say went to the points 3, 3. This would be vector 3, 3, and I had the vector. Let's say that's negative 4, 4. Now you might see this already, but if you look at this carefully and you're to draw a triangle in between them, if you would actually draw a hypothetical triangle in between them, you would notice that there's a right angle right here. This right here becomes a right angle. Now what would happen if we took the dot product of these two vectors? Well, if we took the dot product of these two vectors, you'd get negative 4, 4, dot producted with 3, 3. That would give us negative 12 plus 12, which would give us, well, that would just give us 0, which is interesting. And this is a fact that is true about all vectors that come together to make a right angle in between them. If the angle becomes a right, if the angle between them becomes a right angle, then we can say that it's going to the dot product of those two vectors will become 0. And this is what we call orthogonal vectors. We say orthogonal vectors have a dot product of 0. Fair enough. Now, when you look at this word orthogonal might seem daunting and might seem strange, but it's simply, literally, all it means is angles comprised of right angles, or comprised of right angles. So anything that we say is orthogonal, we say is comprised of right angles. So it might seem like some weird voodoo like term, but it is literally just means it's made of right angles. So we'd say that if you have a dot product of 0, they are made of right angles, which means, well, they're orthogonal. Great. Well, if we want to put this into practice, let's see if we can prove that certain vectors are orthogonal. Let's look at problem number 23. 23 says, prove that the vectors u and v are orthogonal. So we have a vector that's 2, 3, and we have a vector, let's call it w, equals 3 halves, and negative 1. Well, we know that if we took the dot product of these two vectors, they would become orthogonal. They would have, well, if they're truly orthogonal, their dot product would be 0. So if we want to prove that they are orthogonal, we would have to say that u times the dot product of u and w equals 0. Let's go and see if this is correct. So let's plug in u and w. So we have 2, 3. I should probably be using different color, but it's too late now. I'm sorry if I any confusion. Equal times, or the dot product of that with 3 halves and negative 1 equals 0. All right. Let's go ahead and work this out. So we're gonna multiply the x's together. Multiplying the x's gives us 2 times 3 over 2, which that just becomes, those cancel out, so we just get 3 plus 3 times a negative 1, that'd be a negative 3 equals 0. Oh, and that just cancels out to be 0 equals 0. So that's good. We have a solid proof that these are now orthogonal vectors. Excellent. So that's really all orthogonal vectors are, and that's where we're at. There's one more major concept we need to cover in this lesson. The last major concept is this idea of vector projection. Now, vector projection says this. If I have two vectors, let's say I've got the vector. We have these axes. Let's draw our axes. Our axes right here. All right. Now let's say I had a vector. I had a vector that was, let's use an orange vector. And it went all the way down, let's say over here. And we had another vector, maybe a smaller vector, that kind of went up a bit. Let's say up here. So let's say this is roughly, I don't know, the vector, this would be the vector 0, 6, or 6, 0. 6, 0. And this would be the vector, I don't know, it's about 4, 4, 4. Great. Now, if I was to say I wanted to project one vector onto another, here's just what I'm saying. I'm saying, let's say I wanted to see how much this purple vector impacts the orange vector. Let's say how much does it actually affect the orange vector if we were to put them together. To think about this in a more concrete way, let's think about it this way. Let's say I drew let's use gold, like a happy little sun. Yeah, let's say it's a really nice happy sun right above. Oh, this is a really hairy sun, right above the points, and perpendicular to the orange vector. Let's say if I do this, what kind of shadow would it cast? What kind of shadow would it project onto the orange vector? Well, we know that if it shined onto this purple vector, it would kind of shine something like this, something around this, and cast all of this onto the orange vector. So all of this orange vector here would be covered in shadowy darkness, even though it's yellow and supposed to be lit up. Whereas the rest of it would be fine lit up by the sun. And this is what we see. So if we were to try to see how much was covered, how much was of this purple vector was projected onto the orange vector, we could draw a new vector and say this is the projected vector. This is let's actually, if we call this purple vector U and we call the orange vector W, if we wanted to, this yellow vector would be the projection of U onto W. And that's what we'd call it. Well, an interesting property about this projected vector is that it is comprised of right angles. Let's use a color to show that, hey, this is comprised of a right angle. The sun is always going to be at a place where it's going to shine and cast a shadow that creates a distinctly right angle on this. So if we had two other vectors, say like this and like that, the shadow would cast and still create a right angle. It would still create a perfectly right angle every single time. So the sun would be around here or so. But that's the point. We're getting a right angle to see how much does it project onto that one. And so let's and you might say, oh well, that's well and good, but that's not really useful, is it? No, actually it is. This is a very useful tool to see. And in order to demonstrate this, well, before actually I get ahead of myself, let me give you the formula of what this is. This is something for your notebook. The projection of U onto W equals the dot product of U and W over the magnitude of W squared times W. Now, for the sake of your time, I'm not going to go into a full-on proof as to why this works the way it does, but you can kind of see just intuitively, hey, we're taking this U here and we're multiplying it. We're multiplying it by this W like twice. We're multiplying W by twice, and we're dividing it by W like twice. And so it's really just U, but just morphed into W. Now you might be saying at this point, well, Mr. Jurashek, this is all well and good. I can project of one vector onto another, but this really isn't useful. It doesn't even make much sense. Well, I will give you an example that's actually really useful. It actually makes a whole lot of sense, and it's actually really, really practical in our everyday lives. Travel with me over to Taylor University, where we live literally in the middle of a cornfield. And in this cornfield, there's a lot of different things out there. Sometimes you run across a couple cows. Yeah, this is my drawing of a cow. Don't judge. All right, here we go. Yeah, I'm sure you can do better. Yeah, I know. So, I have a cow, and I'm with my buddies. Here's me and my buddies. we're here, and we're trying to strategize the best way to make this cow's life miserable. That's right. So he's dozing off happily in sleep. He's dozing off happily in sleep. And that is there we go. There we go. This is oh, I just carved up his head. Okay. So the point is we're gonna lunge at this that each of us is gonna lunge at this cow and we're gonna try to knock him over onto his side because we are wonderful people and this is what we do when we have nothing else to do with our lives. Alright. So I could either go straight at him and just lunge at him and push him over that way, or that might be my strategy. I'm just gonna fly at him. I'm gonna go. I'm gonna run. I'm gonna sprint, and at the last minute, I'm gonna jump into the air and just lunge at him and just fly like a speeding bullet out his face or maybe his upper torso. And I'm gonna create a bunch of energy this way. I'd probably if I would have created an amount of energy, I'd hit. Well, let's say this creates a vector. Let's say that'd be 5, 0. So I hit straight horizontally, but that gives me a direct hit of 5 units of force and just vertically. Let's say another friend of mine decides to have the same idea, except he's instead of lunging at this guy sideways, he says, "I'm gonna lunge at him upwards. I'm gonna sprint at him. I'm gonna just run like the Dickens. And the last minute, I'm just gonna jump upward. I'm gonna dive upwards into his gut to see if I can push him over that way. So we're gonna jump upwards and just take him out that way, hit him over. And so that'll create a shockwave up in this direction. I'll give him the and he hits it so hard it's like it's in this direction. If the force goes up to say a vector of 3, 3, 4, that sounds reasonable. And what you'll notice is this is the kind of force vector that comes out. Remember the vector has direction and magnitude, as our Despicable Me characters so carefully said it. So if we did this of I would have a magnitude. The amount of force I would end up putting onto this cow would be, well, that'd be the magnitude of this side vector here. This side vector. That would be a magnitude of, well, that'd be the square root of 25 squared plus 0 squared. That'd be 5. And if I was to do the magnitude, my friend's magnitude, the amount of force he ends up putting on this cow is, well, let's say that'd be the square root of 9 plus 16. Again, I just squared 3 and 4, add them together. That equals square root of 25, which equals 5. Great, so we put the same amount of force into this cow. And so, but who has a better chance of actually knocking this dude over? This is where projecting vectors comes in and saves the day, right? Here's what we're gonna do. We're gonna go ahead and see, put a little sun up here, and see how much rightward force this upward vector has. So if I were to convert this upward vector to rightward force, how much force would it actually have? Let's make a right angle here, and let's see how much force it would create. And so we use our vector properties. We'll use the projection of, let's say this is friend, and this is me. So we're going to use the projection of friend. Let's just use F for short, onto me. So that would equal vector friend, the dot product of vector friend and vector me over, let's see, we're putting onto vector me, so it'd be the magnitude of vector me squared. Let's see, times vector me. Excellent. We're gonna do something here. So the dot product of vector friend and vector me, my friend's vector and my vector, that'd be the x's multiplied together. That would be 3 times 5. It'd be 15. So let's see if we do 15, and the product of the y's, that'd be 15 plus 4 times 0, which is just 0, all over the magnitude of my vector. Oh no, magnitude of my vector. Magnitude of my vector is 5. So it'd be 5 squared times 5. Excellent. So if we did this, we would say it's 15 plus 0. So it'd be it's equal to 15 over 25 times 5. Well, these two, we can go ahead and cancel out a little bit here. We can say this would equal 15 over 5, and that would be well, it'd be 3. That'd be 3. Let's see, is that right? Yeah, 5, 10, 15. Excellent. I just made this up right now, so I think this will work. So my vector, so his vector, if you were to project his vector onto my vector, and this kind of makes sense, it would create a vector, a total force of 3. What this means is that if he lunges upward, my friend lunges upward, and it only hits on the side, he's only going to create 3 units of force, the equivalent of 3 units of force on knocking this cow over. The rest is just hitting him upwards. And hitting a cow upwards by a unit of 4 units is not going to be very helpful. You want to hit him sideways to knock him over. So my strategy of just coming full force and just lunging through the air like a ninja kick, man, that's gonna knock this cow over. So now we have a strategy to really do some good stuff and do some good deeds in this world. And I hope you're happy, because this is where we've come to in pre-calculus. Anyway, that's literally all we have. I hope you found this helpful.